going to explain to you why you should be excited about this. I guess the motivation for this is a lot of what we're going to do is related to gravitational wave searches and PTA work. And MeerTime's a fantastic instrument for this. And a lot of the activities and data analysis is really focused on most of the pulsar timing. So I thought I'd give you a bit of an overview of the pulsars. So about me, I was born in a small town in Canada. I did my PhD in the US. I moved to Sydney. I thought I'd be in Australia for a year, and I've been there over a decade. And now I'm in faculty at the Swindon in Melbourne. This is me snowshoeing in Canada, that's my dad. And one of my main research interests are timing and also pulsars. Search for and do very interested study gravitational waves. And also I do work with FRBs as well. So I thought we'd do a very light introduction to gravitational waves. Discuss how pulsar timing waves work, the science of PTAs, and then talk a bit about the MeerTime pulsar timing wave project. And I hope at the end of the talk you'll realize that none of these gravitational waves are where it's at. So gravitational waves are fluctuations in space-time. The distortions you can think of as causing space to stretch and shrink. And this causes clocks to tick faster or slower. And we've heard today about pulsars, and pulsars are fantastic clocks. And if we see differences in the arrival times of any clock, we can start putting them up to the gravitational waves. The gravitational wave spectrum, we can think of with facilities having a few different components. We talked about not mentioned LIGO, and LIGO, of course. LIGO is sensitive to the in spirals of double neutron stars and solar mass black holes, of course, and that's at higher frequencies. There's going to be an experiment in 2030. It's called Pulsar, which is a space-based interferometer, and it's going to be able to be sensitive to more massive black holes, including potentially the in spiral of supermassive black holes. And then there's the PTA band. So the PTA band is at low frequencies. We're going to talk about frequencies of nanohertz. And we think that, we'll discuss a bit more about the most likely signals there, but it's thought that stochastic backgrounds from binary supermassive black holes is the most likely signature. So, as I mentioned, we'll skip through this pretty quickly here. All of the slides will be shared, and you can look at them in more detail. I know it's the end of the day, I don't want to do all that math right now. But basically, the way gravitational waves work is that they are perturbations to the metric, and these perturbations propagate into the light, and that effectively causes an effective redshift or blue shift of the signal from the pulsar, if it depending on exactly happening. One of the interesting things about this is that it really depends on the value of that perturbation at the position of the pulsar and the position of the Earth. So what you see is actually, if you have a simple gravitational wave, you're seeing the effect of what's called the Pulsar, which is at earlier time, and the return, which is at later time. And potentially, if you had a gravitational wave source that was evolving, you're going to see the signature of the source, such as the binary supermassive black hole, 1,000 or 4,000 years in the past, right? These pulsars are at distances of about a kiloparsec, right? And kiloparsec is 4,000. So we don't measure the redshifts, we measure the residuals, and one of the key take-homes today, I think, should be that the pulsar timing technique is amazing because we can track the rotation of the pulsars. We'll get to that in a minute. And that basically means that we get to integrate, over time, the effects of those redshifts. And that can accumulate, and that does accumulate, and we'll show that in a moment. So we talked a bit about these nanohertz gravitational waves as mathematical things, but they're they're actually physical things. And the most physically motivated is binary supermassive black holes. We'll discuss that in a bit. But there's other sorts of things we think about as well. Things that are, people talk about string theory as a way to solve unify gravity and the other fundamental forces. Those strings communicate. And there's other early universe signatures as well that potentially produce gravitational waves. Those are probably less astrophysically motivated, but always should be keeping in mind when we see things. If we see something that's odd, consider the possibilities. Well, having priors, Bayesian odds, saying that, well, this topic is the most possible scenario. So those are the types of things that can radiate gravitational waves, but we can also think about with respect to signatures it produce. So we can have stochastic backgrounds. This is the cumulative signature of all the gravitational waves ever emitted in the universe, in the visible universe. So that's kind of everything. But then we have other things as well, like single sources. We might just have one source. And then there's other interesting effects related to gravitational wave that we can also be on the lookout for. And it turns out when compact objects merge, you get this thing called gravitational wave memory, which results in a net shift in the metric for all the time. Small effect. So, going into gravitational backgrounds, black holes for why we might expect to be a stochastic background from gravitation, supermassive black holes. We think that black holes form early in the universe as the first galaxies. Galaxies merge, we know that, and after these merge, the galaxies are dynamically dragged to the centers. When they get close to each other, dynamical friction is not the dominant cause for them to be inspiraling. It becomes they become dominated by gravitational emission. Then after the merger, the resultant black hole gains mass through accretion. We know these things called quasars, and that so now you're getting bigger black holes. And this process repeats many times for each correct galaxy. Here's just an example of a hierarchical merger tree where you have a galaxy today and a black hole, and all the galaxy mergers that have existed as it grew and evolved, from versions 10 to now. So on top of this, obviously detecting gravitational waves is pretty awesome. You can put in your favorite adjective there. But you can also think about the astrophysics of this, right? So supermassive black holes are also pretty awesome. You put it in your own adjective there too. And what we think about here is there's really good reason for us to want to care about these things in larger picture astronomy as well. So we want to know how galaxies formed, what galaxies look like today, and what the first galaxies look like. And it's, these supermassive black holes, these are things that go in solar masses, so, maybe 100 million solar masses, so they're pretty big, but there are centers in these galaxies that are, 100 times bigger. So despite that being only a small fraction of the mass of the system, they play profound roles in shaping how galaxies form and evolve. So, and the issue, of course, is that these black holes, in addition, to being, black, are also in the centers of galaxies. So there's lots of stars and gas in between those centers of galaxies and us. So they're very the gravitational waves, of course, pass through it without a hitch, and we can study them in great detail using gravitations. So the issue, of course, with these gravitational waves is that the perturbations we're talking about here are very small. They're not LIGO small. We're the gravitational wave spectrum, but it was like 7 orders of magnitude between the PTA sensitivity and LIGO sensitivity at least. But so what we really need to do is see these things, is to look for sources at large distances. that's where pulsars come in. So, as I said, pulsars are awesome, and timing pulsars is an amazing puzzle and a great tool. So the reason why pulsar timing is so great is that it's peaceful here. So if you looked at this plot here, this is timing residuals from the first millicycle pulsar. And the observation started around 1984, and this data set goes to the end of 2022. And I know that the first observation in the last was this many rotations, right? So we got thousands, millions, billions, right? So 585 billion, 999 million, 381,787 rotations between the first and last. And pulsars like this pulsar, as long as we have radio telescopes, we're going to be able to detect this route. So millicycle pulsars are sensitive to the smallest perturbations. This here, if I was to sort of put the axis down by a factor of 100, or so, 10 to 100, could possibly be a gravitational equivalent data. But this is way loud. This is inconsistent with other pulsars, but we'll look at things like this. And I did an interesting experiment here and order magnitude estimated the strain of this is a gravitational wave. And it turns out that between the first and last observation here, which is about 38 years, that's around 10 to the 9 seconds. And if I call this a millisecond, if I said the strain is delta 2 on t, this is around 10 to the minus 12. The signature we're looking for is a strain is around 10 to the minus 14, 10 to the minus 15. So, I presented you here that hopefully by the end of this talk, this is a gravitation. So this is a plot from Miles' PhD thesis, but this again here is a low frequency time correlated signature that can possibly be a gravitation wave. And we're talking about now changes in path length from the gravitational waves on the orders of a few hundred meters, so the orders of 100 nanoseconds, for objects that are 1,000 light years away, and varying over the course of years to decades. So as I said, the most likely source that we can see is the stochastic background, the superposition of gravitational waves from many sources. The background induces what we call a red power spectrum in the residuals. This is more power at lower frequencies. These things all look, if you look at them, they're kind of like what we call like cubic polynomials. They're not perfect cubics, and that has to do with the way that we fit the data. But what we're showing you here now is some simulated data set where I have pulsars aligned in a ring of the sky. And if you look here, this is the gravitational wave passing by the Earth, the gravitational wave passing by a pulsar, and this is the combination of the two. And you notice here that the signature here becomes like correlated with pulsars that are close to each other, then it becomes decorrelated and flips around and correlates back again. This correlates over 180 degrees, and this is because gravitational waves are quadrupolar. And this quadrupolar nature of gravitational waves is key for us to detect gravitational waves. The gravitational background we characterize by this power law process. We have this amplitude and a spectral index. People think that this amplitude, at the end of the day, you're probably going to forget this number by the time you get your barbecue this evening, by around 10 to the minus 15 to the minus 14. The key point here is that it's perturbations on the orders of tens to hundreds of nanoseconds on time scales of years. So Daniel and Matthew talked about the time precision we can achieve, and for the best pulsars we can get down to tens of nanoseconds, but for many it's hundreds of nanoseconds. So we really need pulsar timing, right? We need to study a bunch of pulsars just to get that sensitivity. There's a lot of things that can affect this amplitude of the signal. And things can get messy. It could be that binaries from massive black holes don't deliberately stall, they don't emit. Or maybe there's a lot of gas in the galaxies, and that ends with the result of not emitting as many gravitational signals as we think. But there's a lot of interesting knobs we can turn when we search gravitational waves and don't see them, but also more excitingly when we search for gravitational waves and then do see them. So the first thing people reckon they'll see when they look for this gravitational wave background is what's called the common red process. So the gravitational background has two contributions, one that has spatial correlation and one that doesn't. And this is the effect of the pulsar current. That these are gravitational waves passing by pulsars thousands of years ago, and they passing by pulsars, one pulsar is 1,000 years ago, the next one is 1,200 years ago. So these signals don't have any correlated component. So what we mean by a common process is something that is statistically identical between the pulsars, but it's different realizations. So you can imagine you flip a coin, heads or tails, it's random. If one person flips one coin, another person flips another coin, they're going to, you say that they both have 50-50 chances. They're not going to have the same, they're independent flips, right? So just an example of what this red signal will look like. Here's time and residuals for some of the data sets. And these are all from the same underlying statistical process. You can see one thing here looks like a kid going this way, another has a kid going the other way, and one looks like it's almost like what we call quasi-periodic. So that's not definitive evidence for a gravitational wave, because other sources of noise can look like that. Pulsars have spin irregularities, and to a certain extent, we expect millicycle pulsars also to have them, despite us hoping that they don't. So what we really need to see is a gravitational wave. So what we're going to do is search for this correlated signature here. And for reasons, because we're looking at the background, this correlation curve doesn't look like a perfect quadrupole, but this is a search, the signature that works looking at. So there's a lot of groups doing this around the world, and there's been efforts that have been going on since the mid-2000s in Europe, North America, and Australia. But there's a lot of interesting projects going on within these new more sensitive telescopes, including with MeerTime. The groups also combine data together as part of an international effort called the International Pulsar Timing. There are some key differences between how gravitational waves are detected and studied in nanohertz frequency gravitational wave land and at LIGO. And one of the key differences is that we need to understand the noise in our data at the same time as we search for the signal itself. And this really is going to, we're going to do a lot of this in some of the tutorials tomorrow on Wednesday. And but this is kind of the key point. So, as I mentioned, here's just an image of like where major facilities are doing this around the world. And recently, research has become more sensitive because of longer timing baselines. The signature we're looking for is this red noise process that gets louder, should get louder the longer we look at it. On top of that, larger samples of pulses are being observed. And then on top of that, we have more sensitive instruments. This is not sensitive telescopes, but just upgraded instrumentation that makes things work. So I'll just say where we're at with different projects around the world. I'm going to compare two projects: the nanograph project in North America and the PPTA project. The nanograph project has seen the strongest evidence of gravitational waves in their data, and the PPTA project is what I'm involved with, and this is analysis of data. So here's just an example of, this is just the observations from the nanograph data set, and you can see here just how much the project's ramped up from 2004 to 2020. And there's a lot more pulses being timed, and that's one of the reasons why this research is more sensitive. We're going to be, the techniques used are the same ones that are going to be, you're going to look at using the same software tools that were done for these searches. Here's the PPTA searches, and again, you can see here that, well, it hasn't been as much of a ramp up number of pulses observed. This is showing you the different colors and frequencies, and you can see here the use of this pulsar wideband system from parts, which has really increased its sensitivity as well. So we'll compare the results, and when we do these comparisons, one thing to keep in mind is that a lot of the pulsatory waves share pulsars. This is because the best pulsars are awesome. We all want to time pulsars to highest precision. We all want, some of us want to be able to report the first sub-nanosecond around time. But we can't. That's why we live here again. It's a dream.
Think of the combined brain power in this room.
Yeah.
3 days.
3 days. I believe, yeah.
Hip-hop history.
So when we compare the results to the data sets, that all the PTAs are finding significant basic evidence for this common process in the data. Again, we can't say the common process is a graphically background, and there's reasons to believe that common property is possible to trick the algorithms instead believing this common process on its own. All is showing what is evidence for helix-bounce correlations, and we'll discuss that in a moment. But I just wanted to show you sort of where things are at with these results and some plots that people look at and go through them and hopefully understand why people do making plots like this. Yeah, I won't go through this. Bayesian model selection is one of the ways people decide whether or not to use this in the data. And I'll hand it over to Matt. We'll put that in Matt's talk tomorrow and the day after, whatever that is, and we can talk about that. So here's your plot now comparing results showing the amplitude of the signal observed, which is AGUV, amplitude here versus gamma. And these are what we call posterior probability distributions. So these are just saying how loud, what's the loudness and sort of redness of the signal in these data sets. The nanograph signal is a bit bluer than the PPTA signal, and the amplitudes are different, well, consistent, but you know, there are some modest differences between them. So you'll see lots of plots like this, and these are plots that are produced after doing Bayesian inference techniques. And these are what we call posterior probability distributions. And another thing people like to look at is what does the signal look like as a function of frequency. So you can go and look at this common noise at different Fourier frequencies. So now you can see here, this is like frequencies in the residual. So these are like nanohertz-like frequencies, 10 to the minus 8.75 hertz. And what you see is that the nanograph signal, if you look at the first few frequency bands, it looks steep, but then it sort of bumps up a bit here. What's causing that is unclear. It could be that there's extra noise in their data. That's not being properly modeled. Whereas the Parkes data set has a much more consistent power law that demonstrates that. As it should be. So, of course, what we want to look for is the correlations. And here's how people make plots showing the cross-correlated power in this data with error bars versus angular separation. And then they overplot what the expected cross-correlated power should be. So what we do here is you can correlate the residuals from pairs of pulsars. You don't have like 13 pulsars, you've got 30 pulsar pairs, you've got hundreds of thousands of pulsar pairs. And then you average them together to spin it up. It's really easy to average all those pulsar pairs to get some optimization. And this is what the Parkes series looks like, and this is what the nanograph looks like. And this is Parkes series closer to 2 sigma, and the nanograph is closer to 4 sigma. And you might ask the question, why is it 4 sigma detection, right? Or why is it 2 sigma detection? And the key point is that there could be other things in our data that could cause there to be correlations. So, really, to be able to say confidently that the detected gravitational wave signal, you need the bar is higher. This isn't, there's other things that can do this, so that's why we need to say, what further switches. What also motivates things is that peak data is kind of weird, that if you were to look at the loudness of the common signal, it's growing with time. So we think of cosmological things and the universe in a universe in 2008 ought to be the same universe in 2016, for given you've got binary supermassive black holes that are inspired over the course of hundreds of millions of years, and you've got a cosmological population. So that's a mystery that we're still trying to understand. Other searches other searches have consistent results with the searches I presented here. Just show these two because of conciseness. So that's where things are at. So where do we want to go? So as I said, detection of the gravitational wave background or gravitational wave period will require convincing a higher threshold for Halle-Sounds correlations. So for existing PTAs, there's a benefit, there's benefits of doing better modeling of the data sets themselves, and also just observing for longer. The existing PTAs can also combine data as part of the IPTA project as well. However, there's other ways to increase sensitivity as well, and that's using new facilities. New facilities, especially with improved instrumentation, and observing more pulsars. So this is really motivates the MeerTime Pulsar Timing project. So we started observing with MeerTime in sort of early 2019. The project has observed probably over 10,000 observations now. We would know it's over 10,000, but the disk and swimmer data go is full, so they have to transfer. Clean your data, delete data, please, if you're on the project. We've been observing just with the LBAN system, and just inside a full load. This is just an example here of the observations that I've been undertaking. You can see here we started off with the models doing sort of census, and then we really ramped up our kids in 2020. So we've done lots of work. The first thing we did was figure out what pulsars are pulsar timing pulsars like MeerTime. And this will also tell us about what pulsars will be good with ESK as well. And we looked at other things as well, and then last year we put together the first data release that I met. One of the things we did is when we do pulsar timing, you need to know what the time is, right? It's kind of obvious, but keeping track of time is important, and keeping track of time on fast time scales and slow time scales is important. So what we can do is we can see how well we can recover the MeerTime clock. So there's a set of measures on site that are designed to deliver us times at, as Matthew said, nanosecond accuracy. And we do a pretty good job of that. There's a bit of a weird patch around here. What that is still a bit of a mystery.
Any ideas?
The interesting thing is that you notice here the blue line is the clock signal itself.
Yeah.
And you can see that these little, the process are then changing the clock, steering the clock. You can see that, so that it tells us how much you're steering the clock, changing the lasers basically. And you can see that they're doing a lot of changes around the time.
So are we going to do that in check?
So
Every 200 days?
yeah, so these things are every 200 days, right? So one of the requirements is that the time that is being given to the data is kept within 200 nanoseconds of coordinated time, like
So what do they do that digital?
So
To laser?
it changes the way it changes the script, basically. So anyways, we'll skip through the equations here, but one of the things to point out is that you really benefit in pulsar timing arrays from timing large number of pulsars. So really, timing them, if the common signal is gravitational background, timing pulsars to 5-10 pulsars to 10 nanoseconds is not the best way to get detect gravitations. So the strategy was trying to make pulsars as possible to some microsecond precision. So whereas projects like at Parks time pulsars for over an hour, the nanograph times at 20 minutes, hope that we should be able to be sensitive, the project will be sensitive to gravitational lasers. So if you looked at basically how we expect sensitivity to grow with time, you can see here that the MeerTime project grows very quickly with time because of the large number of pulses that are observed. So, so basically the key take-home message here is that MeerTime is essentially sensitive very shortly, and will also be contributing to the IPA project. So the black line here is the IPA project. So we've done, for the noise analysis, spatial plotting again, the signature that I showed earlier, and if you look at the amplitude spectrum index of this is similar but louder to the carbon noise of the red fields. We'll go through a bit about the complexities of noise.
So wait, what did you show on my book?
This is showing you the time residuals for the best pulsar and pulsar.
For that?
For the best pulsar and pulsar.
So only one pulsar?
This is only one pulsar. And this is just the time residuals, right? So with one pulsar, you don't know if that's gravitational waves or anything, right? So you need to see the correlation. But it's promising that something that's kind of about the properties of gravitational waves is appearing in the MeerTime data on short time scales.
Okay, so what alternative information do you have?
The pulsar here is rotating spin noise. Pulsars don't have to work spin regularly. There could be issues that there's more noise that's misspecified, that there's some weird effect in the ISM that we're not studying.
As in like a cloud or something?
Yeah, some sort of cloud or stuff that's really strange. Or it could be, such as slides ago. Sorry, go back. Right, here we go. This here, the clock hasn't random drift in it that we're not floating at.
So that's not, I mean,
Yeah, it's not the same thing. Sorry, it's not that it doesn't look the same, but you have to be wary, and that's why you have star content.
But I mean, if you watch it with Gravitational time, you get another, I mean, that's going to take what it might be.
Yeah, exactly. Anyway, so if you do the noise analysis for the MeerTime data, the first thing that one can see is that there's something in the data that's common, but keep in mind that common noise doesn't necessarily mean gravitation. So things are looking very promising for your guy. And for gravitational efforts around the world. So I think it's going to be a very exciting time for the field. We're going to assume the field's going to transition from this long slog as people doing this for over 20 years of trying to search for gravitational background or search for gravitational waves to start studying it. New facilities like MeerTime are really opening up the field. But now's a really great time to get involved. So through the rest of the workshop, what we're going to do is we're going to look at some of the ways we analyze pulsar timing data. That's all, again, as I said, that's what we're from. That's sort of my bread and butter. So we hope we'll get a flavor for how to analyze data. Hopefully, you'll find that the entry, it's not a black belt field. The entry to getting involved is not impossible to overcome, and that pulsars are a joy to time, and that pulsars, as Evan said very eloquently, pulsars are awesome. I'll leave it there. Thank you.
Thanks a lot. Questions for Ryan? Yes, sir.
Okay.
Thanks. I've got a couple of questions. The first, I think you may have covered, but I'm trying to just link it in my head. To go from observation with such precision on the time. To only having a modest detection of that heading down. I was just wondering, those error bars,
Yeah.
How do we go from such precise timings to, is there something in the correlation that, maybe you can just,
Yeah, so I didn't really get into the theory of how we do it. So I guess first thing is that even though the timing is like of tens of nanoseconds, over the course of five years or whatever the contribution of gravitational waves to the data sets on the same order. But the one major issue is that we don't know the distances to pulsars. So that means that if I had just, one a single Earth pulsar baseline, the correlated signal, and the common signal on that is a signal ratio of about half almost, right? So if I looked at correlating two pulsar pairs, the pair only has a maximum correlation of half. So there's a self noise that does it, right? So it's those two captures.
so if we had really precise positional data, like distances to the pulsars, would that improve the...
that would be, exactly. And there are some two pulsars where we have that before. Damage is responsible for both those things. But, so like you need to have distance to sub, like if you're looking for gravitational waves with a period of 10 years, you need to have a sub-light 10-year distance. Or, and so there's a couple of sub-light year pulsar distances. So we hope to find more. The other exciting thing you can do actually is that if you had a single gravitational wave source in your data, you can potentially solve for all the distances to all pulsars. So I would agree.
Could I ask one more? So this is about the gravitational wave background. I was wondering how well that was, and is it...
Sorry, I missed that.
Sure, I was just about the gravitational wave background. I was wondering how well modeled that was, and if it's the contribution of all gravitational wave sources. I was wondering, I don't know if this is a silly question or not, but if there was any expectation of trying to look at black holes to contribute to that background. I don't know, I've never heard of it contributing to that.
So on the second part, the gravitational waves that we're sensitive to are gravitational waves that have periods of frequencies of generations. So primary black holes are much lower mass. So when they're at that, if they're orbiting at that period, they would just move to strong emitters of gravitational waves, so that's less likely. There's a lot that can go into that, even if you've got an astrophysical gravitational wave background, because there's a lot of just like super fast. It's like, what's the initial mass of those seed black holes, right? What's the merger of galaxies? How much mass do galaxies, how much mass do black holes get through accretion through this process, right? So there's a lot of knobs to twiddle, which is good and exciting. There's also a possibility, again, that there's like gas and stars and centers of galaxies causing the signal, and if that was the case, then the gravitational background need not be a power. It could have some funny break in it with show you where sort of you actually get become gravitationally bright.
I just want to ask, in the Pulsar Timing is a stationary process. Follow a certain time.
So the time stationary, what was it?
Stationary process. So does it follow a certain time?
So like we consider them to be stationary processes in the sense that we expect what if I had this in this 10 years, in the next 10 years, it should have the same statistical properties. It doesn't mean that it can have correlations in it, right? So that's sort of what we mean by stationary.
But you always also choose the pulse laws that remain the same. So like this is selection effect, 4 pulse laws that are stationary that you use to do the time with. Like a millisecond pulse law. There's a pulse law with low red noise, you use the don't use it.
That's true as well. I mean, that's another motivation for trying to deploy the signal. But we would consider that part, that noise in the core timing pulsars to be stationary as well, because we expect the same statistical properties of the signal of that red noise data from, this 10 years in next years. But that's a big assumption as well.
And also, is it possible to test the significance of imbalances?
Yeah, I mean, I guess like one, we say I said it's stationary, but they go all the way back to this here's arguing against this. Because if it was stationary, I would expect it. This is showing you basically the loudness of the signal. You can see here that early on there was the signal was nothing was found, but what was not found was inconsistent with what was seen. So anyways, we don't know that could be an issue of what we call misspecification. So one of the key points when we're doing pulsar timing analysis is to have robust and accurate models of all the processes that are there. And that could be the case. So this is, if you look at this plot, you can just say, oh, the gravitational wave background is non-stationary. But it could be that there's some other non-stationary process in the data that we're not modeling. So it's where we probably need to do detailed investigations. And you need more people thinking about what could possibly be in existence.
Okay, I think that's a wrap.